taking time out of your day, whether it be from a chemistry class or from your PE, your wellness class, to be here. We are delighted to welcome Dr. Ellen Anderson, mostly retired professor from the University of St. Joseph, to speak about some topics of science and in chemistry. Participation is encouraged throughout the whole presentation. And without further ado, Dr. Anderson.
Thank you. I don't know if Mr. Wilcox has told you, but my granddaughter goes to school here. She's a junior. And a couple years ago, when I retired, I was looking for things to keep my brain active and to keep my hand in the chemistry. And I thought, oh, well, I'll go to Berlin High. She was taking chemistry at the time. And I'll go to Berlin High and see if the chemistry department's interested. And I looked up the teachers of chemistry at Berlin High, and I went, Brendan Wilcox. That name sounds really familiar. And I went, oh yeah. He happened to be a student of mine. I had him as a grad student about 10, 12 years ago. And so it made an instant connection. It was kind of cool to now be teaching his students after I taught him. And yes, he did extremely well with me. You can talk to him about that. I teach biochemistry, which is not his specialty, but he still did great. I'm not talking about biochemistry today. I'm going to be talking about some experiments that were carried out 100 years ago or more. And when I used to teach general chemistry in college, I like to try to personalize it, not just talk about the results and the chemistry aspect of it, but the people who did the experiments and some of the stories related to their carrying out these experiments. And one of the things I wanted to try to point out to the students was that it's not written in stone. Science is not written in stone. You, looking back at it and learning it, it's like, oh yeah, this is the way it's always been. No, 100 years ago, there was a very different view of the atom. In fact, about 150 years ago, they didn't even believe, there was an argument in the literature as to whether atoms even existed. And in the late 1800s, they thought they knew everything there was to know about the atom, and there was nothing left to learn, and what were they going to do for the rest of eternity when they already knew everything. And then, as what often happens is, someone does a new experiment, and you can't explain the results with the current theory. And it blows the entire thing out of the water, and you've got to rethink the way you look at whatever it is you happen to be looking at. In this case, we're talking about atomic structure. And over this period of time of about 30 years that I'm going to talk about, they kept doing new experiments. And they kept having to change the way they thought about things. And it boggled the mind. So we're going to start with J.J. Thomson, and I'm going to point out in many cases, these are all people who won the Nobel Prize at one point or another. J.J. Thomson, you could sort of call him maybe the father of modern physics. He won the Nobel Prize in Physics in 1906. 6 of the students who worked under him won the Nobel Prize in Physics. 2 of his students won the Nobel Prize in Chemistry, and his son shared the Nobel Prize in Physics as well. So obviously, he himself was brilliant, and he picked brilliant students to work for him who also won Nobel Prizes for the work that they did. So what did he do? Well, his experiments used what's known as a cathode ray tube. And Mr. Wilcox brought me an example of one. We weren't able to set it up to actually work, but this is what it looks like. It's a glass tube that would be filled with a gas, and then most of the gas pumped out, so you nearly had a vacuum inside. You would have it connected up to electrodes, and you would turn on the electricity, and what you would see You don't have a pointer, do you? I didn't bring one. And I don't. Well, I'll point on the board.
Charge on the thing that you can move this out of the way without having to trip yourself.
So you hook it up, and what you start to see are these ghostly, eerie rays. And Thomson did a whole series of experiments, and what he discovered is that these were particles. And he applied electrical and magnetic fields to these particles, and what he saw was that the particles were deflected in various directions. So for instance, if he turned on the positive plate here and the negative plate here, these rays were deflected upward. So what does that tell you about the nature of these particles? They were attracted to this plate and repelled by the negative plate. It has a negative charge, right? Because opposites attract and like charges repel. So obviously these particles must be negatively charged because they're attracted to the positive plate and repelled by the negative plate. Now I'm not sure I can see if I can get this website to work.
Should open up a browser.
It's taking its time.
Click on the X, it'll kill the thing that's on top of it, and then you can run those simulations.
So here's just a website showing you a Crookes tube, a cathode ray tube, and here we have our plates, and there's our ray of electrons, or excuse me, particles, whatever they are. And if we charge the plates, so at the top, we make the top positive, you can bend it in that direction. If you make the top negative, you bend it in the opposite direction. Okay, how do I get back to the...
You, on the bottom, yep. Not that one, though.
Oh,
That one. And then
Okay.
play. Press the play button in the middle, at the top.
I do not use a Mac, so I have a PC. All right, so based on this experiment, he was able to calculate a mass to charge ratio for these little tiny particles. And he estimated that these particles were about the 1,000th the size of a hydrogen atom. Now, up until this point, atomic theory said the atom was the smallest particle, that you couldn't break it apart. And here he was breaking apart the atoms and identifying particles that were 1,000th the size of an atom. And he said, this is a quote from him, "We have in the cathode rays matter a new state in which the subdivision of matter is carried much further. This matter being the substance from which chemical elements are built up." So he blew out of the water the idea that atoms were not divisible. And of course, we know now, of course, there are smaller particles than atoms. There are electrons and other particles that we'll talk about. But this is over 100 years ago, and this is how they first discovered that there were electrons. So the cathode rays, he discovered, were negatively charged particles. Eventually, they were called electrons. And by varying the electric and electrical and magnetic fields that he applied to the cathode ray tube, he was able to calculate a charge to mass ratio. But he was not able to calculate either the charge or the mass. Now, serendipity is a wonderful word. I have a whole talk on serendipity in science. And I taught a class a couple of times on serendipity in science. Serendipity is finding things by accident. So you're looking for one thing, and something else happens, and you go, oh, what is that? And then you go off and study that in particular. William Röntgen discovered X-rays serendipitously, by accident. He won the first Nobel Prize in 1901. He was making use of these same cathode ray tubes. And he was studying how they caused fluorescence on the end of the tube. And he had, outside of the tube, these screens covered with a material that fluoresced. And what he discovered is that even when he covered the tube with cardboard and he looked at the screen that was covered with the barium compound, it fluoresced even when it was several feet away from the tube. So something was escaping from the tube and causing the screen to fluoresce. And he called these things X-rays, because you know what they were. And then he started trying to take pictures of things with the X-rays, and on the left, you can see that he took an X-ray. Here's one of the very first X-rays. This is his wife's hand. So his wife's hand with her ring, and there's his wife. And he was, now of course they didn't have any idea of the fact that X-rays were dangerous. And so I don't know whether he ended up having any health effects from playing with this stuff, but he discovered what was called X-rays. Now, equally serendipitous was the discovery of radioactivity. And Henri Becquerel in 1896 discovered something interesting as well. He was looking at uranium salts, so uranium ores, and he found that if you put a sample of uranium on a photographic plate, he got a picture of the ore. Only they thought that they required sunlight, that you had to have the ore sitting in the sun, and then it absorbed the energy from the sunlight, and then if you put the uranium on the plate, you got this lovely picture of the uranium. Well then, as often happens, the sun didn't shine. So he wrapped up the uranium in a piece of paper, and he stuck it in a drawer, sitting on top of a plate, and it hadn't been in the sun for days. And when he took the plate out, lo and behold, the plate had a picture of the uranium, even though there was no sunshine. And so he realized that the energy given off by the uranium had nothing to do with the sun, that it was inherent to the structure of the uranium itself. He was a physicist. He won the Nobel Prize in 1903 in physics, but he was not a chemist, so he didn't really know how to deal with the uranium. So he had a friend, Pierre Curie, who was a chemist, and he gave Pierre Curie the sample of uranium to study and extract the material. Pierre Curie had his wife, first a student, who then he married, Marie Curie, who actually did all the work. And she isolated the uranium, and then she discovered that the ore that they were using had more radioactivity in it than just could be accounted for by the uranium. And she actually discovered 2 new elements, which she got to name. If you discover a new element, you get to name it. So she named one polonium because she was from Poland, and the other one radium because it radiated. And Pierre, Marie, and Henri Becquerel shared the Nobel Prize in 1903. Now, everybody thought Pierre was the brains of the outfit, and she was just doing all the grunt work. And then he was killed in a traffic accident. He was run over by a cart in Paris, very young. She was widowed. Lo and behold, she continued to do a lot more work. And she was actually the brains of the operation, not him. She was the first woman to win a Nobel Prize. She is the first person to win 2 Nobel Prizes. She won this one in 1903 in physics, and then she won one in chemistry. And she was brilliant. Obviously, almost everybody has heard of the person of Marie Curie. However, she was never elected to the Paris French Academy of Sciences because she was a woman. No women were allowed in the Academy of Sciences, despite the fact that she had won 2 Nobel Prizes. Her daughter also won a Nobel Prize along with her husband. So again, comes in the genes. Any questions? So in 1899, Ernest Rutherford started to work with these radioactive materials, and he wanted to characterize the radioactivity in more detail. Ernest Rutherford was from New Zealand. I was in New Zealand this past spring. It is the most wonderful country, if you ever get a chance. It's really far away. We took a non-stop flight home from Auckland to New York, 15 and a half hours in an airplane. Yeah, it's the other side of the world, but gorgeous, gorgeous country. He was the first Oceanian person from that part of the world to win a Nobel Prize, and all of his work was carried out. He actually did this work that he won the Nobel Prize for in Canada. So he was the first person to win a Nobel Prize to do the work in Canada. So what did he do? He had this experimental setup, a lead block to block the radioactivity from going in lots of different directions. The radioactive substance that he used was polonium, which was one of the new elements discovered by Marie Curie. And he focused the rays through a set of electrical plates, and he discovered that the radioactivity was split into 3 parts, and it was caused glow on the photographic plate. And he, not knowing what they were, just named them alpha, beta, gamma. Anybody know where alpha, beta, gamma comes from? First 3 letters of the Greek alphabet. You'll discover if you take more chemistry that chemists love to use the Greek alphabet over and over again, and you'll find alpha, beta, gamma used in lots of different venues. It's not just the same, not just here. He found with these photographic plates that the alpha rays were bent downward, the beta rays were bent upwards, and the gamma rays didn't get deflected at all. So what can you say about alpha rays? They must have a positive charge, right? They're attracted to the negative plate, repelled by the positive plate. What about beta rays? You. Negative, okay, because they're attracted to the positive and repelled by the negative. So we have positive alpha rays, negative beta rays. What about gamma? They must be neutral. They're not affected. So as you said, the gamma rays are positive. The beta rays are negative, and they are particles. And the gamma rays are neutral and not particles. They were discovered not to be particles. Rutherford won the Nobel Prize for this work in 1908. And in 1900, someone else, Paul Viard, characterized the gamma rays as high energy electromagnetic radiation. Turns out that the beta rays were characterized as electrons. So this radioactive material, polonium, spit out high-speed electrons. Those were the beta rays. They spit out high-speed alpha particles. Those alpha particles they discovered down the road were helium nuclei. And then they discovered that the gamma rays were electromagnetic radiation. So, electromagnetic radiation, energy that travels through space in waves and has associated with it an electrical field and a magnetic field. And we know, you're familiar with a lot of these. Visible light is an example of electromagnetic radiation. Very narrow range that we can actually see with our eye. But you also have X-rays, gamma rays, ultraviolet, infrared, microwaves, radio waves. And here they are characterized by the length of their wavelength. The wavelength is the distance from the top of one wave to the top of another wave. And radio waves have very long wavelengths, the wavelengths of somewhere between a building and the size of a human being. Microwaves are shorter, infrared even shorter. Visible light in this region here, 10 to the minus fifth meters. Ultraviolet, even shorter, the size of a protozoa. X-rays in the range of a molecular size, and gamma rays even shorter. Now just to point out some other experiments that were used carrying out light. Something called the line spectra, which Mr. Wilkos tells me you've seen. So if you take light from the sun or from a light that you've seen, visible light, and you pass it through a prism, you get what's called a continuous spectrum, right? Example of a continuous spectrum. Anybody seen an example of a continuous spectrum? What happens if you have rain in one direction and sun in another? Rainbow. Okay, so a rainbow is a continuous spectrum. It's visible light passed through the water droplets in the air, and we get a continuous spectrum. The one color bleeds into the next color, into the next color, without any gaps. If, on the other hand, you take a gas and pass electrical power through it, instead of getting a continuous spectrum, you get what's called a line spectrum. This happens to be a hydrogen lamp, and what you get are just individual lines. And different elements give you different line spectra. The first one was hydrogen. It looked sort of purpley. This is neon. Yes, neon lights make use of this very type of experiment. It's not shown here, but here's hydrogen. You can see calcium is quite different. This is mercury. You'll notice mercury has these very two strong lines. If you drive down the road and you see street lights that look sort of purpley instead of yellow, if they're yellowish, they're sodium lights. If they're purpley, they're mercury lights. So what you're looking at is the line spectra in the visible region for the various elements that are used inside the lamp. Well, they didn't have any explanation at the time, 1844. Why do you see a line spectra instead of a continuous spectrum? No explanation. It was quite a few years later before someone was able to explain why you get this kind of line spectrum. We'll come back to them. The lamps get really hot really fast. Robert Millikan won the Nobel Prize in Physics in 1923. He was one of the first American scientists to win the Nobel Prize. Most of his experimental work was carried out by his graduate student, Harvey Fletcher. And this is often the case, most often the case, with professors. The graduate students are the people who do the work. They don't always get the credit that they should get. Sometimes they end up sharing in the award or the renown that their professor gets, but not always. And in this case, I discovered a really kind of ugly story about Robert Millikan. Most of the work was carried out by Harvey Fletcher. Millikan took sole credit for the work that we're going to talk about. He won the Nobel Prize for the work, even though he didn't do the work. Now, as the professor, he directed the work. He helped the student understand the work, but he didn't do the physical work, and maybe even didn't do the initial theory behind it. He basically threatened his graduate student with not giving him his PhD if he didn't let him take sole credit. That's pretty ugly. I would have been furious if my professor, when I was doing my PhD work, had demanded to have sole credit for everything I did. He didn't do it, I did it. He made a deal with Harvey Fletcher. If Harvey Fletcher let him take sole credit for the work that we're going to mention in a few minutes, that he could give him his PhD for a different set of experiments. And Harvey Fletcher agreed and kept this deal a secret till he died. It didn't come out until his papers were looked at after he died. Of course, Millikan won the Nobel Prize for the work he did. Harvey Fletcher did not get his name on the Nobel Prize for the work he did, and the other experiments were not deemed Nobel Prize worthy. So he never got the Nobel Prize, even though he deserved it. This is not the first time that that has happened. This is not something I'm going to talk about in this set of experiments, but you all know about the DNA double helix, right? Everybody knows what the DNA looks like. Anybody know who won the Nobel Prize for the structure of DNA?
Next year, you might have a class.
Watson and Crick. Watson and Crick won the Nobel Prize for the structure, the double helix of the DNA, which we base all of our understanding of DNA on now. They only were able to do that because they saw X-ray photographs that were taken by Rosalind Franklin. They basically stole her pictures, never acknowledged her work, and they won the Nobel Prize. Now, sadly, by the time the Nobel Prize was given, Rosalind Franklin had died, and Nobel Prize is only given to living scientists, not to people who have previously died. So she couldn't have won the Nobel Prize at that point anyway, but they never acknowledged her work. So basically they stole her work, based their answers on her work, and never acknowledged it. Ugh. Okay, so what did he do? It's called the Millikan oil drop experiment, except Millikan didn't do it. But if you look it up, it's always called the Millikan oil drop experiment. And here's the actual apparatus. And what he did was had a source of little oil drops, his little atomizer over there, where he sprayed oil drops into this apparatus. And then he had these electrical plates, which he could charge up. And he had a source of ionizing radiation such that he would create charged particles that would stick to the oil drops. And then what he did is visually, through the little telescope there, watch how quickly or slowly the oil drops fell. So first he looked at how did they fall in the absence of a charge on the plates, and then he tuned up the electrical plates, and he watched what happened to the rate of fall of the oil drops. And what he found was that when he tuned up the plates as they are, negative here, positive there, the oil drops fell more slowly. So what does it tell you about the charge on the electrical on the droplets? Negative plate, positive plate. They became negatively charged. Based on this experiment, he was able to calculate the charge on the electron. So this ionizing radiation caused electrons to be released from the gas that was inside this apparatus. The electrons stuck to the oil drops, and if you turned on the electrical plates and repelled, they would slow the rate of fall, and based on the rate of fall, he was able to calculate the charge on the electron. And he found that it was negative. And then using that charge and Thomson's charge to mass ratio, he was able to calculate the mass of an electron. 9.1 times 10 to the minus 28th grams. Little tiny particle. Now, Rutherford did a few more experiments for which he is remembered, and Geiger and Marsden were his students, and he was freely acknowledged their participation in these experiments. And his experiments are known as the gold foil experiments. Carried out 1908 to 1913, so just over 100 years ago. And what did he do? He had an alpha particle emitter, so a radioactive substance that emitted alpha particles. And remember, alpha particles are positively charged. And he focused the beam on a very, very thin metal foil. So the foil was, if you take a metal and pound it, you can make an extremely thin metal foil. And then he had a detecting screen surrounding that would glow when the alpha particles would strike it. And the results of this experiment were shocking. They expected that the alpha particles would go straight through. What they found was that most of the particles went straight through. So, the other side. Some of them were slightly deflected. So the path was bent. However, several of them were completely reflected back towards the source. Rutherford's response to this was about as credible if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So there was something about the structure of this gold foil that was not expected. So again, the results on the right, most of the particles went straight through as if the foil wasn't even there. Some of them were slightly deflected, and occasionally, 1 in 20,000 bounced straight back. So what did Rutherford decide based on this? And this is no surprise to us. But at that time, this was completely unexpected. The fact that most of them went straight through tells you that the gold foil, most of it is empty space. Wait a minute, empty space? It's a gold foil. But if these particles were able to go through without tearing a hole, they didn't tear a hole in the foil. It was as if the foil weren't even there. The fact that they are some of them are slightly deflected, the alpha particles are positive, says there's some positive part of the alpha foil that's repelling those alpha particles. And the fact that you've got some that reflect right back at you, it says that most of the mass of the gold foil atoms is located in one small, tiny area. And if your alpha particle hits that small area, it's like running into a brick wall and you're bounced back off. This led Rutherford to create what we know now as the nuclear model of the atom, the fact that all of the positive charge and most of the mass of an atom is in a very small area inside the nucleus, surrounded by mostly empty space where you find the teeny tiny little electrons, which have basically little mass compared to the nucleus. If your nucleus were the size of a tennis ball, the edge of an average atom would be about a mile away. And out there in that mile of space would be a bunch of little fleas. Your elephant is sitting in the middle with all the mass. And out there in that space are these little electrons, which are hard to find and don't weigh much of anything. Yes, they have weight, but compared to the nucleus, you know, if you've got an elephant with a flea on the back, you can weigh the elephant and you could put 100 fleas and you wouldn't know there were any fleas there because the comparison of the weight would be so great. We take this model for granted. This was a shocking revelation to say that the atom is mostly empty space and that the mass is all in a little tiny nucleus. Now, what about protons? Rutherford also discovered the proton, and he bombarded nitrogen atoms with alpha particles. He liked using those alpha particles. Once he discovered what they were, he was like, oh, what can we do with these things? And he discovered that when he bombarded nitrogen with alpha particles, that hydrogen nuclei were released, the same charge and mass that a hydrogen atom was released from the nitrogen. So he postulated that the hydrogen nucleus, the proton, must be found in nitrogen. We must conclude that the nitrogen atom disintegrated and that the hydrogen atom, which is liberated, formed a constituent part of the nitrogen nucleus. So now we've got electrons, and we've got protons. What's missing? Neutrons. Protons and electrons are really much easier to discover and to characterize because they're charged. So it's easier to do experiments with particles that are charged because we can set up our electrical plates, our magnetic plates, and we can deflect things, and we can measure their mass and their charge. Neutrons are neutral. Pay no attention to all that, so it's much more difficult. Neutrons were not discovered till 1932, even though these gold foil experiments and this discovery of protons carried out in the teens, they knew that there was something there, but they couldn't characterize it. Because they measured an alpha particle and all the charge could be accounted for. There were 2 protons, charge of +2. But the mass was bigger than 2 protons. So it suggested that there was a neutral particle, but it wasn't until 1932 that James Chadwick was actually able to do the experiments, which were much more complex, to prove that there was a neutron, what it was, its mass, its lack of charge. And he won the Nobel Prize in 1935. Now, just to remind you, we talked about light as a wave, energy traveling through space as a wave. Physics, there are lots and lots. I mean, I'm sure when you take physics, you will do experiments with light. When you look at its properties and reflection of light, diffraction of light, that depend on it as a wave. Everybody knew light was a wave. Of course light's a wave. Electrons are particles, light's a wave. Until more experiments were carried out and could not be explained by light as a wave or as electrons as particles. So, what's called the photoelectric effect, first observed in 1887 by Hertz. And if you shine light on a metallic surface, you can get electrons emitted from the surface. This is how electric doors, opening, sliding doors, you go to Target, and there's a little thing up there that you walk under, and when you walk under that, the door opens. That depends on this effect. That is emitting electrons. When you break this pattern, the door opens. And the number of electrons that are emitted depends on the intensity. How bright is the light? Is it a weak light? Is it a bright light? So the number of electrons. However, if you use a certain, this effect only occurs if you use wavelength, energy of a wavelength, frequency, energy high enough. Below that energy, nothing happens. So if you're to use ultraviolet light of the right wavelength, this occurs, but if you go down to visible light, it doesn't occur. And the energy with which these are emitted depends on the wavelength. So the wavelength of the light is important, not just how bright the light is. Couldn't explain the experiment. Energy, light as a wave, you should have been only dependent on the intensity. How bright is the light? A tuner, when you walk in, you've got a dimmer. When you turn it one way, it gets brighter. You turn it the other way, it gets dimmer. That's what we mean by intensity. You're not changing what color the light is. All you're doing is making it brighter or darker. Couldn't explain it until Albert Einstein, for which he won his Nobel Prize in 1905, first Nobel Prize. And he proposed that light actually exists as particles called photons, which was mind-blowing. Been talking about light as wave for centuries, and now you're talking about light as particles, and the energy is quantized of those particles, meaning they come in little packets. They come in this wave, this much energy, this much energy, this much energy. Describing light as photons, particles, he was able to explain the photoelectric effect. So the question is light a wave or is light particle? Now here's another property of waves. And whether you're talking about water waves or light waves, if you set up two waves and the waves run into each other, you get what's called a diffraction pattern. And where the waves, the heights, the two waves are high together, the wave gets even higher. If one wave is high and the other wave is low, they cancel each other out. And that's shown in this region here, where it gets brighter and then dark, depending on how the waves run into each other. The same is true for light. They either get brighter or cancel each other out. These kind of diffraction patterns were well known. Someone in 1927, Davison, Germer, and G.P. Thomson, this is J.J. Thomson's son, were the one we started with, took electrons and did the same kind of experiment here, where they shine light on a barrier with holes in it so that it created two waves that interfered with each other, and got the diffraction pattern from waves. They did the same experiment with electrons. Now, electrons are what? Electrons are particles, right? We know they're charged. We know they have a mass. They're tiny, but they're still particles. And what you expect for particles when you have this double slit is some of the particles go through one slit and some of the particles go through the other slit. And if you have a detector over here, you're going to have particles detected in one spot and in the other. Instead, what they saw was a diffraction pattern. If you're seeing a diffraction pattern, you're seeing the results of two waves interfering with each other. But these are electrons. They're particles, aren't they? But we're getting a diffraction pattern that you only get from waves. So which is it? Are electrons particles or electrons waves? Talk about blowing the minds of the scientists. So now we've got light as waves, but some experiments can only be explained if light is particles. We've got electrons that are particles, but some experiments can only be explained if they're waves. So which is it? Particle or wave? Obviously, the answer, well, not obviously, but the answer to that is they are both. They have wave properties. Light has wave properties, and light has particle properties. Electrons have particle properties, and electrons have wave properties. It depends on the experiment you carry out. So they're basically, it's not that there are particles over here and waves over here, and never the twain shall meet, but rather waves and particles are on a spectrum, and it depends on how you look at them, what results you get. So for instance, can everybody see both the rabbit and the duck? Depends on how you look at it, right? If you sort of focus over here, it looks like, to me, that gives me the duck. If I focus over there, I see the rabbit ears. The same is true. These are, optical illusions. You could look them up on the web anywhere. So here, if you focus up here, you can see the young woman. That's her chin. There's her nose, her eyes, her hair. However, if you sort of focus down there, there's the old woman. There's her chin, and that's her nose. So the one picture is both. It depends on how you look at it. What experiment do you do in order to explain, to get the explanation that you need? So both light and electrons act as both particles and waves. They have both particle and wave properties that need to be taken into account when you describe the structure of an atom. Not what was expected 50 years earlier. I don't think so. Good question. What would they be if they weren't neither? I don't know. So, coming down towards the end here, Niels Bohr won the Nobel Prize in 1922, and he expanded on the model of the atom that Rutherford had created. Rutherford had talked about a nuclear model. He had talked about the protons and neutrons being in the nucleus and the electrons out there somewhere. Niels Bohr created a model that you all probably learned in 3rd grade, where you have the electrons circling the nucleus on circular orbits, like the sun and our solar system, so sort of the solar system model of the atom. And he won the Nobel Prize for this, and this model didn't last very long. Even though they teach it still, it's not correct. It's easy to understand, but it's totally not correct. There are some parts of it that are correct, but electrons do not move in circular orbits. However, he had circular orbits, and the energy of the electron is quantized, meaning it only can be on the orbit, not anywhere in between the orbits. So the energy of the electrons related to the circular motion of the electrical charge, and so it can only be here or here or here, not anywhere in between. And why did he say that? It went back to our line spectra. And he actually could calculate the positions of the lines for the hydrogen atom. And what he said was that the electrons would start in one orbit. When you send the electricity through them, the electrons would jump to a higher orbit because you gave them energy. and then they would fall back to a lower orbit, giving off energy. And because they could only exist here or here, they could only give off the amount of energy that is related to the distance between those two orbits. So one line would be related to that distance, another line would be related to that distance, another one might be related from there to there. Shown here, the electron falling back from 3 to 2 gives off a certain amount of energy, and that's related to the line seen in the line spectrum. He created mathematical equations that allowed him to calculate the actual positions of the visible lines in the hydrogen line spectra. Wow. He really understood the structure of the hydrogen atom. However, he couldn't calculate all of the hydrogen spectrum, and he couldn't calculate the spectrum for anything other than hydrogen. A theory that only works for hydrogen is not very useful when we have now 118, 117 other elements. So what was the fatal flaw? The fatal flaw was that the electrons don't move in circular orbits. So all those little, I don't know whether in third grade or some grade, you built some model of the atom with your electrons, moving in circular orbits. Yeah, no. So he did this in the early 20s, and almost immediately after winning the Nobel Prize, his theory was blown out of the water. Just a little bit more about Niels Bohr, just kind of interesting. He was Danish, and in the 1930s, he actually helped refugees from Germany escape Nazism. In 1943, he himself escaped to Sweden because he was going to be arrested by the Nazis. So he also had a son who won the Nobel Prize in 1975. So there are a number of parents and children who won Nobel Prizes over the years. So our last scientist is Edwin Schrödinger, and he calculated the energy of the electrons in an atom based on their wave properties. So instead of saying, looking at electrons like planets, where you can calculate where they are at any given moment. How many of you know about the eclipse that's going to occur in about a month on April 8th? Total solar eclipse. My husband and I are eclipse chasers. He's seen 21, I've seen 20. We've traveled the world in order to see eclipses. When I said I was in New Zealand in April, we had gone to Western Australia to see the eclipse, and it was one of the prettiest we've ever seen. And then because we were that far away from home and we'd never been to New Zealand, we went to New Zealand as well. But we're going to see the next eclipse, and we've already scheduled a eclipse trip. Well, we haven't yet booked, but for 2026 is the next eclipse, and 2027, we've already got that one booked. So how is it that we can calculate eclipses? Well, they can calculate exactly we know exactly where the Earth is, we know exactly where the moon is, we know how fast they're moving, we know their orbits, and so the scientists can calculate exactly where the sun will be, where the moon will be, where the Earth will be at any given time, and can calculate with extreme precision when the sun, the moon, and the Earth will line up to give you a solar eclipse, or sun, Earth, moon to give you a lunar eclipse. Can't do that with electrons because you can't calculate both the energy and the position of an electron with great precision simultaneously. You can calculate one but not the other. If you calculate one very accurately, the energy, you can't calculate the position. If you calculate the position, you can't calculate the energy. Well, Schrödinger, using the fact that electrons have wave properties, created an equation using those wave properties of an electron to calculate the energy of an electron quite accurately. So he was able to calculate line spectra, energy for not just hydrogen, but more complex atoms. And because he was able to calculate the energy, we can't know anything about the position of an electron. All we can say is the electron is, we can talk about probabilities with electrons. It's a high probability of finding the electron in this place at this time, but we don't know exactly where it is at any given moment, and we have no idea how it gets from point A to point B. We don't know its path, we just know its energy. So instead of talking about orbits, we talk about orbitals. Regions of space where there's a high probability of finding an electron. And he takes into account attraction between the electrons in the nucleus and the repulsion between electrons in his calculation. It's actually a rather interesting, you can do this calculation. I did this calculation twice, once in undergrad and once in grad school. Using calculus, you can quite readily calculate the energy of an electron in hydrogen. Going beyond hydrogen, it becomes much more complex. I don't know if you can do it with one electron, like a helium with one electron, or a carbon with one electron, which of course carbon doesn't have just one electron, but you can calculate that kind of more complex fairly simply. Once you start adding more electrons, it went beyond my ability to do that kind of math, but at any rate. Have you talked yet about orbitals? All right, so here is just a picture of an electron cloud. An orbital, a high probability of finding the electron within this region. Here we have an s orbital, spherical. Here we have a p orbital, two regions of space with a node in between where there's no probability. We have no idea where the electron is at any given moment within that region of space. We have no idea how it moves. We just know that 90% of the time you're going to find it here. 90% of the time you'll find it there. Very different way of looking at atomic structure from where we started, where we didn't even know there were any smaller particles inside an atom. We now have a nucleus with positive and neutral particles. That has most of the mass, small region of space. We have large regions outside the nucleus, where we have electrons that act as both particles and waves. We know that they're there. We can calculate their energy. We can calculate line spectra, but we have no idea how they move. It would be like, there's a high probability that you are going to go from here to your next class, but we have no way of knowing necessarily how you're going to get from here to there. Your path is not fixed, it's not determined, and one day you might go this way and another day you might go that way. We don't know your path, we just know where we're going to find you with a high probability.
It's a nice opportunity for a meta moment as you think about your future, whether it be in science or something else, to not know exactly where your path will lead, and take every opportunity you can to learn new things and that you might not know where it will help you, what path or will help you on.
So just to finish up, here's the atom through time. John Dalton, atom's smallest particle, indivisible. J.J. Thomson, 1904, we've got protons and neutrons, protons, electrons, somewhere embedded in this space. Ernest Rutherford, we've got the protons in a nucleus and the electrons out there somewhere. Niels Bohr, 1913, we've got the protons in the nucleus and we've got the electrons moving in circular orbits around the nucleus. And 1926, we've got Edwin Schrödinger, where we know that the electrons are out there somewhere, but we don't know where. Any questions?
Fortunate are we to have about 10 minutes for you guys to ask questions, make comments, or connections. Share thoughts. Go ahead, Tyler.
How many Nobel Prizes are there?
Well, there are maybe types, you mean, or people? Well, there's Nobel Prize in chemistry, Nobel Prize in physics, Nobel Prize in medicine and physiology, Nobel Prize in literature, Nobel Peace Prize. I think that might be it. So it might be 5. I might be missing one, but those are the ones I remember. And sadly, most of them have been given to men. So there's a whole group. And interestingly enough, actually, one of the topics I was looking at for another talk I'm giving somewhere else was about people who should have won the Nobel Prize but didn't, like Rosalind Franklin or Harvey Fletcher. And it was an article I found on the web written about maybe 5 or 6 years ago, people who should have won but didn't. And one of the people who were listed in that website won the Nobel Prize this past year for her work on mRNA vaccines, which are the type of her work led to the type of vaccines that are used for COVID-19. So it was like, okay, he said, this person said this woman should win the Nobel Prize, and lo and behold, she did. It was the Nobel Prize in medicine and physiology. Yes?
What inspired you to become a science professor?
I had a fabulous chemistry teacher in high school. And in fact, the American Chemical Society does a survey every, once in a while. I've seen it done at least 3 or 4 times in my 40 years as a chemist. And they ask professional chemists, why did you become a chemist? Whether you became a professor or whether, and almost 100% of people say because they had a really good high school chemistry teacher, or the chemistry professor they had at the beginning of their freshman year was really, really good, and that's what turned them on to chemistry. In my case, it was my high school chemistry teacher. And I knew once I took a class from her that I wanted to be a teacher. And I actually, we had, as a senior, we had to do some kind of a senior project. And my project was that I taught for a month one of the chemistry classes for my teacher. She gave me free rein, and I had a topic, and I taught, and I discovered I really loved doing it. Initially, when I went to college, I wanted to be a high school teacher. And I did my student teaching in the inner city in Providence. I went to Brown University, and I did my student teaching at an inner city school down the street. And it was not a happy experience, particularly. And I decided I didn't want to deal with classroom management issues, which I had to do. And maybe I would have, if I had had a different classroom and a different environment, I would have felt differently. And at that point, I decided I wanted to teach college instead of high school because I wanted to just be able to teach and not have to worry about anything else. And one of my worst chemistry experiences was one time when I was teaching at UConn, the branch in West Hartford, and I had students in the classroom that I had classroom management issues with, and I thought, you are freshmen in college, what is the matter with you? So at any rate, it was not fun.
What did you guys think about the idea that science is not stuck and stagnant and that there's changeability in, we think things are set as they are and everyone understands everything, and we have these aha moments or these moments that explode our understanding. What kind of revelation did that have with you, or what kind of resonation did that have with you?
People are always discovering new things all the time.
They are discovering new things, and the issue, of course, is that they'll do some experiment and they can't explain it. And so then you have to go back and rethink, what do I know? How do I know?
Make sure your model matches your understanding, like in principles, right?
It was very frustrating when I was doing my research as a PhD student. I was working with an enzyme called beta-lactamase, which is the enzyme that bacteria spit out into their environment that destroys penicillin. So it's the reason they are penicillin resistant. And we were looking at how does this enzyme work with the aim of trying to shut the enzyme down so that the bacteria can't destroy the penicillin. And I was working with two different bacteria, B. cereus and Staph aureus. And B. cereus was the enzyme that my professor had been working with for years, and it was the one he was most interested in. And we kept doing these experiments, trying to describe the detailed mechanism by which this enzyme worked. Every time I'd do the experiments, we couldn't explain them. We'd get results, we couldn't explain the results. So finally he said, let's try this with Staph aureus, an enzyme from a different bacterium. Same enzyme, but slightly different bacteria. And I spent 6 months doing experiments, and every experiment worked. Everything worked. The mathematical models I created explained everything. It was wonderful. So we'd learn stuff, and we'd go back to B. cereus to try to figure out what was going on with B. cereus. I spent a whole summer with him saying, do one more experiment. Just one more experiment. And I'd do one more experiment, it would raise more questions. We never answered the questions. Never.
What I love about that story is that as you go through this, you have to trust the process that you're doing, and then trust your ability to conduct a thoughtful experiment and really look to carve out the niche. And so even though there is what some of us would call failure in there, there's really success in how you target your questions and what you do. Nice anecdote.
So it was very frustrating. Finally, at the end of the summer, my professor said, oh, just write it up and go away, which is, of course, what I wanted to do. So.
What kind of chemistry students comprehend?
I would like to say the quantum chemistry that I was talking about with Schrodinger, but oftentimes the thing that I found when I was teaching it that the students had the most difficulty with was the kinetics, which is the study of the rates at which chemistry reactions occur. And they had great deal of, it's very calculable, but they had great difficulty understanding that.